Uh, so welcome back, everyone. So let's get started. So welcome back from Thanksgiving break. Hopefully everyone had a nice Thanksgiving. Maybe was able to get some time off, do something fun, or so to catch up on some work, as I know happens in college. So sometimes. It's great. So we are going to be talking today about the Perceptron algorithm. This is one of kind of the oldest techniques to learn a classifier in machine learning, and it is something that will help us learn a linear classifier that we talked about in the last lecture. But as we'll see, it also will kind of help us prepare to understand how to do these nonlinear classifiers, which I think kind of introducing some of the duality concepts that will show up in the perceptron algorithm will make it easier to understand how to do these nonlinear classifiers, especially to understand what's going on. And then this algorithm will also kind of show up. It kind of is how one layer of like a neural net is kind of working. So this will help to add some intuition there as well. All right, great. Okay, so great. So we are near the end of the semester. We have 3 more lectures of actual kind of content on the class, and then there'll be a review at the end of at the end. I'll probably try and cover some kind of material that the class kind of found more challenging this semester, and I will probably also try and go through the practice exam I have linked down here at the bottom right of the screen. So that, again, that exam has more sort of questions on it than will be on your actual final, but kind of is of the nature of the sort of things you could be asked. So we'll try and basically, I think we can go through that in the lecture, depending on how much I talk about other stuff as well in the last review lecture. So the grades for homework 4 were posted. These were kind of I guess the lowest average grades of the semester for the class on a homework assignment. This is kind of standard in this class. The homework 4 is usually the hardest one for for a few reasons. I expect the grades for homework 5 will be higher. Part of the reason homework 4 was a little bit lower is a number of people didn't turn them in or turned them in late, but also I think people generally struggle with that. One issue that came up a lot in the gradient descent section was people were formulating the function they were trying to minimize as actually the actual prediction function, not the error of that, not y minus what you predicted, but the actual just prediction function. And so this was a common mistake many people make. If people have specific questions about that, can maybe go go over something quickly. Otherwise, we can review this. So that'll probably be some of this stuff that we will review it in the last lecture. Okay, so I know that part was challenging. For those of you who kind of were able to figure this out or mostly do it, that is really kind of one of the core things of how most kind of machine learning algorithms actually run. So, try and look at the feedback in the homework and see if you can understand that, because this is a really kind of the important kind of central computational step in most machine learning algorithms. So the other thing is homework 5 has been posted. It's not due until December 10th. Feel free to turn it this one in earlier. So I think after today's lecture, you should have everything you need to solve it, maybe with the exception of one question will come on Thursday. I did realize, or TA Peter realized, there was one other change. I think you can answer and get the same answer even without making this change, but this should be a less than 2 instead of a less than 1 there. So there's one more small correction on that homework. I think if you solved it with the less than 1, you might actually get roughly the same answer. Okay, and then quiz 5 will be on Thursday. Quiz 5 will cover all of clustering. So 3 lectures on clustering and the first 2 lectures on classification. Okay, so we won't get into the kernels and the SVM stuff, which we will talk about in class on Thursday. I can spend some time on Thursday to review a few concepts as well if you have some questions. But that will be the final quiz, and we're still tuning it. But I hope everyone can do well on this quiz. So, okay, great. Any questions on the schedule? All right, so let's get into the lecture. So great. So we were talking about the classification problem, and so let's just review kind of how to think about this again. Pen's working, okay. So let's think we have data, and so we have these points, and think of each of these points as being like an applicant. All right, and they want to get admitted to the U, and the U wants to admit people who they think will succeed in the program. And let's say the admission standard is based on 2 properties. This might be the GPA, so in high school. Okay, and this would be like the rank of the high school. All right, like you can get a GPA in your high school, but some high schools are ranked higher than other high schools. And if you get a higher GPA at that high school, it might be more meaningful than one at a lower ranked high school, right? I'm not totally sure if this is how everything actually works. And so probably if you have a high GPA, it's good. They want to admit a student with a high GPA from a high school that's ranked high, and maybe admit these are students who succeeded in the past, and these are students with, say, lower GPAs, maybe from a lower ranked high school, and these are students we don't want to admit, for instance, okay? And so so maybe in the past they've admitted students from these schools, and these are students who did not do as well, and these are students who did great. The ones with the pluses did great. And what they'd like to do is figure out what to do about a new student, so a new applicant. Okay, so a new applicant, they want to predict, is this student going to do well if they were admitted, right? And so the standard way to do this is to try and build a function, right? And the idea is the simplest way to make a prediction is to draw a line between the students who did well in red pluses or did not do well, so with the minuses. And then if the new applicant is on this side of this line, where we have a sidedness based on a normal vector, then you'd use this function to make a prediction on the student, right? And so this is kind of what a linear classifier is doing with the line, and so kind of trying to find this line which is separating these points, right? So this is the goal, and we'll encode our data with coordinates. In this case, they have 2 dimensions and a sign, a plus or a minus, right? So our data is x, which is going to be, in this case, our d. It could have been r2, and it corresponds with a y, which is going to be a subset of -1. So +1, right? So each data point, this might be x1 and y1 equals plus, or so +1 here, right? And so we have this, and the x describes the encoding, and the y describes the plus or the minus, and we'd like to find this linear classifier. And as we've learned over the semester, these objects, which have these nice kind of geometric analogs, we can encode these using parameters, right? So this W is W1, W2, and we set that the norm of W is equal to 1. So it's just telling us a direction. And we also need to have some sort of offset, which is B, which is going to be the distance from the origin in the direction of W. It's going to tell us this offset, right? And so we can encode this function with these 3 parameters, W1, W2, and B, and we'd like to learn these parameters, right? And so in the last lecture, we talked about how to encode this by coming up with this convex loss function, which penalized points based on if they were on the wrong side. If we had a classifier described by W1, W2, and B, where a point was on the wrong side of the classifier, the -1 was on the other side of it, then that would be a penalty. And even if it was to make it convex, we have to say if it was too close to the boundary, there would also be some sort of penalty. And then we could optimize this using gradient descent. What we're going to talk about in this lecture is instead an algorithm which is going to be a little bit more concrete, that we'll be actually able to see and understand the physical steps it takes. And it's going to work exactly in this sort of setting. The key thing the key transformation we need is that we're going to think of alpha as this parameterization of, as we'll see, is we'll incorporate B, which is kind of alpha 0, W1 and W2, alpha 1, alpha 2, right? So it's going to be this 3-dimensional vector, and we're going to have a function G of alpha. It's going to taking an x, and it's going to apply a so dot product to 1x. Okay, so I've concatenated a 1 on the front of x here, right? And so the 1 is going to be multiplying by the b and the dot product, right? And the alpha is the w1, w2 are multiplying by the x. You take this dot product. This will describe the description of a linear classifier. I can describe it under this linear model again. I've written it again as an inner product because we're going to think of generalizing this notion of an inner product in the next lecture to describe things like polynomial classification or classification with kernels, like Gaussian kernels. And it'll just generalize this notion of this inner product here. Okay. So, all right, so let's talk about the perceptron algorithm. And before we talk about it, I want to say about some requirements of the perceptron algorithm. Turns out the perceptron algorithm is not quite as general as this gradient descent based classification technique. Turns out it'll be almost as general, but there's going to be there'll be 3 requirements we need, and one of them is going to be slightly restrictive. And we'll see that if you're dealing with kernels, then it's not really a restriction, but in the linear case, it's going to be a restriction. So the 3 requirements of it. So the first one is that we're going to assume that the separator goes through is going to go through the origin. Okay, so this is a picture where again we have these plus points and we have these minus points, and we're going to assume that the separator we find needs to go through the origin here. Okay, so this means effectively that the offset b equals to 0. Okay, so we're going to assume this is going to simplify the way we can describe the algorithm. There's going to be a nice kind of duality between points and vectors we're going to use, and it's going to kind of make this assumption. This is not really that restrictive, and the reason why is we can, if we just concatenate that 1 on front, just like we did with like regression, it can solve this problem. All right, so let me try and draw a picture again in 1D to give you a sense of what is going on here. Okay, so I want the data here, and let's say the origin 0, the origin is here, right? So if I try to draw a linear separator on this data, it has to go through the origin. I'm kind of in trouble because one of the pluses is on the wrong side, but the idea is if I instead think about that all the data points has an extra coordinate, which is 1, well now, right, extra coordinate, which is 1, well now the origin is here, right? So new is down here. It's not kind of in the middle of the points. It's shifted at 0 because now kind of this coordinate, this added coordinate here is 0, and all the points have a value of 1. And so what I can do, and I can basically always do this, is now I can draw my separator that is going through the origin and still is perfectly separating the points. Okay, so if I add this extra coordinate, as long as there exists some separator in this plane, and this could be higher dimensional as well. This could be multi-dimensional, all the points on kind of this lifted up one plane. As long as there exists a perfect separator here, then if I shift it, but it's not going through the origin, as long as I add this extra coordinate, I can always kind of, I get more flexibility with my separator, and I can still guarantee that it can be separated, right? So, and I can still basically do as good as I was doing before. So, assuming that the offset that the separator goes to the origin is not really that much a restriction, I can just add one coordinate like I did before in the case of regression. Okay. Yeah.
So it's doing that better than like trying to center the data.
Yeah, if you center the data, actually even look at this data. So when I drew, if I centered it, it might not, the origin might still be left at this plus point. Right, so the centering is not guaranteed to get this right. Yeah, so generally, if you're trying to do unsupervised stuff with an L2 kind of goal, this sum of squared goals, then centering by taking that, like removing the average is a good idea. But if you're doing a supervised approach, often adding a coordinate of 1 seems to be kind of the idea that is cleaning things up. You could probably go through the mechanics of this in some way without doing this, and it would end up being the same thing, but this will just be simpler to think about. We're going to ignore the offset, maybe pretend we added a 1 coordinate, and just assume the separator has to go to the origin. Okay, so the second thing is we're going to assume all xi in x have xi, the norm of xi is less than or equal to 1. Okay, so all my points, basically this is going to say that there's some circle and all my points have to lie in the circle here. Okay, so I can just set xi equals to xi divided by, I can figure out whichever point has the largest norm, and I can divide all the points by this, right? I can just shrink them down to do this. This isn't really required. It's going to show up in the, it just shows up in the analysis. Okay, so this will simplify when we show why the perceptron algorithm works. It'll be simpler to think about this case. So we can always just shrink them down. In some cases, when we deal with kernels, this will be a natural property that just happens with the data. Okay, but if not, we can shrink it, and the algorithm will still work the same way, but how fast it will work will depend on a parameter that's assuming this property, that all the points are within a ball of radius 1. Okay, so these first two properties are just going to be to simplify thinking about what's going on. Pretty much, we can deal with them. The third one is actually a restriction of the perceptron algorithm. You can only run it if xy is separable. Okay, there exists a perfect separator. Okay, so this means that if I have data that looks like right, if my data looks like this picture over here, right, there's no way I can draw a line that separates all the plus points from the minus points here. Okay, there's not a way I can do this with a line. So this is, these are not, these points are going to be not separable. And so the perceptron algorithm is going to have problems with these points. It's kind of going to go to an infinite loop or something weird like that. We'll see that. Yeah. So if we're doing the linear version of perceptron, which what we'll do in this class, then it needs to be a linear separator. If we're doing a kernel version of the perceptron, including like a polynomial kernel, then it needs to be separable with the polynomial kernel, or with the, or if we use the Gaussian kernel. So if you use a polynomial kernel, or if we use a nonlinear classifier, we might be able to separate these points, and then you can run the perceptron algorithm and something weird won't happen. In fact, you'll be able to show if you use a kernel separator and you set the parameters right, you can always find a separator of the points as long as you don't have two directly on top of each other with different signs. So in that way, in the general version of it, what that we'll kind of think about on Thursday, then this isn't really a problem, but for the linear case, this is a problem. And we'll actually see why, and the analysis of why it works will depend on how separable this data is. Okay, so this is an important assumption, that it only works if the data is going to be so separable. Okay, great. So these are requirements of the algorithm. So now we have, now I can talk about the actual, so algorithm, right, we're going to have as the input, x and y, or each xi is going to be so less than 1, and y is -1 plus 1. Okay, and so perceptron algorithm. Okay, again, like all algorithms we're going to talk about in this class, is going to be extremely short and simple. Let's kind of write it down, and then we can think about what it's doing. First step is to initialize. Again, the output is going to be a W, right? And so such that yi xi dot, so W is always greater than 0. Okay? If you remember this form, right? So I want the inner product of any point with a positive label. If yi is positive, then I want the inner product of xi and w, right? The w is the normal of my classifier, right? So again, the picture is going to look like this. This is my linear classifier. It's separable. There's some normal direction, and I can think of this w as coming out of the origin. Okay, so now I can just think of this. It's described just by this normal vector coming out of the origin. If the dot product with x is positive, it better have a positive sign. If the dot product between x and w is negative, well, then I have a negative sign. So either way, then I'm going to get that data expression for all the data points is going to be greater than 0. Okay. All right. Okay. So I'm going to initialize. Okay. I'm going to set my w as yi times xi for any xi yi in xy. Okay, so I'm going to initialize w actually as any of these data points. Oh, and we'll also have at the end we'll actually normalize w, but we'll just normalize this. Okay, so I'm going to start by picking any data point. This is a lowercase xi, right? I'm going to take any data point and I'm going to multiply it by its sign, right? So if I picked one of the x data points, okay, so my initial guess of, so w might be exactly one of those data points, right? Where this guy is xi and its sign is positive. So I get the data point. If I picked one of the negatively labeled data points as the first one, well, then I would have looked at the vector towards it, and then I would have taken the negation of it, right? So I'm kind of pointing towards one of the positive points or away from one of the negative points. Okay. So that seems like a good start, right? That's kind of intuitively what we want. But I need to ensure that this works for all the data points. You can imagine that if I drew this line through here, right, this separator line, it's not always working here, right? It's not working in all the cases. So I need to make sure this works for all the data points, right? Okay, so I'm just going to have a simple loop I'm going to run through. So for any xi, so yi and xy, so for any of my data points, such that I'm going to have yi dot w xi such that this is less than 0, right? So for any data point with a misclassification, right? So this means it's been, misclassified, right? So if it's been misclassified here, then what am I going to do? I'm going to update. W is going to get w plus yi xi. Okay, so I'm just going to add one of these other vectors onto w. Okay. And if it's a negatively labeled point, well, then I'm going to subtract it instead, right? So that's this kind of that's why we use -1 +1 for y and the value for y instead of 0, 1. It allows this to do these kind of neat kind of tricks here. Okay, and so this is the whole algorithm until either no some misclassified points, no misclassified points, or t steps. I can either run it for a fixed number of steps or until no misclassified points, and then I'm going to return w divided by the norm of w, right? So I want it to be, so it's a unit vector at the end. The vector will keep getting bigger and bigger otherwise, right? Every time I'm adding another vector to it, it's going to kind of be getting further and further away from the origin. As we'll see, it will be getting not too far from the origin, which is why this is going to work. Okay. All right, so this is the whole algorithm. Yeah. So I'm going to go and check all of the points, right? So typically, actually, the way this is going to be implemented is I'm going to kind of maybe I would like randomize the order of the points. If not, people just go at them in order, and you cycle through all the points, and you keep track of the last point that you updated. Okay, and I'm gonna go through the list of points until I find one that has been misclassified. And if I loop around again and I get back to the last point that was misclassified, then I'm done, right? So I just need to keep a pointer to the last misclassified one or an index, and then I can do this like modular loop through here. I might go through the points multiple times, but kind of like incremental gradient descent or stochastic gradient descent, this was a predecessor of all those things. You might not need to go through all the points before it actually stops. To know that you're done, that you have no more misclassified points, you'll have to check all of them. But as we'll see, we'll be able to, if you know something else about the data, which you may not know till you run the algorithm, you can say, well, if I do T steps, actually this steps is the T, so so these updates. So I could wait until I've updated the vector at most, so T times. And this will say, if I've made T of these updates, maybe 10 or 20, then I can say, well, I have some kind of, at some point I will have stopped. I don't, if I know something about what's called the margin of the data, which we'll talk about next, then you can say, if I know the margin is going to be large enough, then I don't need to keep going after this many steps. I know I will have classified everything correctly. Yeah, great. There's some variance, which is much less common, that says always find the most misclassified point to do the update with. If you do this, you have to search through all the points every time to figure out which one is the most misclassified. It's kind of hard to figure out the exact most misclassified point without checking everything. But if you do that, you actually get a slightly stronger guarantee. But that was slower because this one just needs to find any misclassified point. So I just kind of looped through this. And if you look in the book, it actually gives some more detailed pseudocode about how to keep track of the counters. I don't think I'll write that up here. But okay, great. So the algorithm, again, is very simple. One thing I want to point out, something that's kind of really important here, is the duality between points xi and and vectors, so w here. This kind of works because the classifier, the normal direction, is the same kind of data format, which is a vector of length d of the data points. Okay, the data points and the normal are both vectors of length d in this case. Okay, and this is what allows this to work. I was able to, also when I do the updates, I have to be able to add a data point onto a vector, right? So these need to be the same length. And this is kind of key in allowing this to work. If the classifier was instead represented by an offset and a vector, so then the dimensions don't match, right? So I can't start them this way. There might be a way to make this work. And as we'll see with the kernel versions of these classifiers, I'm going to have to kind of do some gymnastics kind of with the algebra to kind of get the same property to hold, where the vector and the points kind of have the same representation. Okay, so if you're a computer science major, you're taking computer science courses, the idea, okay, they're both vectors, so I can add them together. It's really stored the same way, should be kind of, okay, that's kind of conceptually maybe is not a problem. If you're into like doing like, so type checking, this one is the the type of object it is a data point, the other one is a classifier. Well, you have to break that notion of type in order to do this, right? If you're coming from physics or other hard sciences where the units are very important, doing this should make you kind of a little uneasy. But again, it's because they have the same representation that this works. There's this kind of duality in the structure. I can represent a classifier basically the same way as I represent one of the data points. And that's what makes this work. Okay. All right, but the algorithm again is pretty easy and straightforward. And in this case, there's nothing really hidden going on here, other than kind of these requirements are kind of hidden here, right? You have to pre-process it with this extra one. That's easy. Maybe you normalize it. We'll see that in the analysis. And it has to be separable to work. If it's not separable, right? If it's not separable, what's going to happen? In that I can always find a misclassified point. If I don't have a good separator, I can always find a misclassified point, and this will be an infinite loop. I have to have maybe after some number of steps, I'll stop. Maybe I put an extra condition in there, but it's not going to have the same guarantees. Yeah.
You run it for like a large T-max steps with like the amount of misclassified points that assume that.
Yeah, what's going to do is it's going to kind of minimize. It's going to kind of give what's called a large margin. It's going to give the most margin for error on the classifier it finds, and that is true if you always find the most misclassified point. If you just do any misclassified point, at some point it will stop, and it won't necessarily give you the best classifier, but it'll give you a classifier. But if you don't have, yeah, and you can think of that as kind of a version of stochastic gradient descent using this. There's a way to formalize that sort of connection, but I'm not going to work through that. Yeah, but you could think of that as kind of, or if you do a random, I guess a randomized point as well. If you do the most misclassified point, there's kind of a different sort of analysis you use. But all right, so in order to understand this, yeah, so let's kind of, in order to understand why this works and kind of what do you find as a good classifier, it'll be important to talk about the margin, okay? Let me draw another picture here. Okay, you have some negative points, and you have a potential classifier like this one, okay? And so what the margin is I think about if I inflated this classifier a little bit on both sides so that there were no points inside those orange lines there, right? So then the margin would be called often as gamma. It's the amount I can kind of offset this decision boundary and not include any of the points, right? I've drawn so that there's one point here, which is exactly on, which is defining this margin. Okay, so I can define this now, so mathematically. So given, and we can define this more generally with a W and a B, then the margin is going to be gamma is going to be equal to the min of xi and yi, which are in the training data, of yi inner product of, or let's see, of B plus the inner product of W comma xi. Okay, so this is the function. This is inside the parentheses is my prediction function. I want to take the sine of, and then so I could think of this as a function which is slicing through this plane, right? So it's going to be large on the plus side. It's coming out of the plane above the pluses, which is a positive region out of the plane, and through the plane behind them where the minus points are, right? And then I'm multiplying by the yi, and that's turning it into kind of this absolute value kind of function, right? So it's it measures the distance from the green line. And I look at all the data points, and I say which one is the closest. Okay, so it's the minimum distance to any of the data points. It's usually defined in this way. This notion where in the version where this inside term is, my g of alpha of xi, right? Then this is typically how the margin is defined with here instead of the minimum distance. That's typically how the margin is defined. When we get to polynomial classifiers, there's actually a distinction in between these two ways of thinking about it. In linear classifiers, it's the same as the distance to the decision boundary. Okay. All right, and so what's also useful to think about is so W star B star is going to be R min over W and B of the min xi, so yi of the yi B plus W xi, right? So if I were to choose the classifier, again, this is parameterized by W and B, which minimizes the margin, right? Then this will give me the this is the max margin classifier. Okay, so let me try and draw what the max margin classifier might look like here. It's going to be something like this. This will be W star B star. This is the max margin classifier. If I were to draw its margin here, okay, the margin, if I did this correct here, should look kind of like this. Right, so this margin is larger, right, with the purple and pink, right? This one has a larger margin than the green and the orange one, right? And then correspondingly, gamma star is equal to min xi, so yi of yi B star plus W star xi, right? So if I took the max margin classifier and calculate the margin, this would be called the max margin, right? So this is now I'm going to have 3 points which are defining it. This would be the max, so margin, okay? And this would be gamma star. Okay, and so as you can imagine, probably finding a max margin classifier would be better than any sort of classifier. If I assume that, you know, maybe there's some noise in the data, or I don't know what to do, one that gives me more separation from the data points is probably more stable. It's probably going to be so more robust. And there's a lot of kind of theory in machine learning that's backed up by evidence empirically that max margin classifiers tend to work better than any classifier. Or if I had one that almost went through one of the data points, that's probably going to be less stable than one that was further from all the data points, but still had as good of a separation. Okay, and you know, something like if you put a loss function, something like a hinge loss or something else, and ran gradient descent, it's probably going to find something like a max margin classifier. It's not guaranteed to. It's not explicitly optimizing that. The perceptron, if I always use the most misclassified point, will actually try and optimize for the max margin classifier. Yeah. Max, yes, good. Yeah. Right, so I want to find the max of the margin. Good. Yes, so the max margin classifier is the one that finds the maximum out of all the possible margins that I could find. Okay, great. Another thing to note, some terminology which maybe will come up a little bit in the next lecture. These items here, these points which are on the margin, these are called the support points. And when we do so, like support vector machines, we'll be kind of identifying these points in some way. These are, the margin is being supported by these points. For linear classifiers, the max margin classifier can always be found by identifying D+1 support points. That's always going to be sufficient to define the max margin classifier. So one thing I could do to solve this is I could actually look at, if I knew it was going to be separable, I could find all subsets of D+1 points, and I could fit those points with the max margin classifier for just those points, which you can define geometrically. And then one of those, whichever one classified all the points and had the largest margin, well, that one would be the max margin sort of separator. That is not typically how people solve this, although if you wanted to solve it kind of optimally, in the worst case, you kind of need to do something like that. Yeah. Okay. Yeah, so support vector classification is often described as support vector machines are basically finding something like the max margin classifier. Yeah, it is. So there's kind of a way that these are often solved either through stochastic gradient descent or through the perceptron algorithm, where we use kind of kernels. And that's typically what it's referred to, but yeah, this is a very similar concept. If you're identifying the support points, then it's often called a support vector machine. As we'll see with if we use kind of radial basis kernels or Gaussian kernels in the next lecture, we will need to work with support points. In this case, we don't need to specifically represent them. But in the case of kernels, we will need to specifically represent those points within the algorithm. Here, they kind of they're showing up in the ideal case, but we don't need to necessarily identify them. The perceptron algorithm, those might be the points that cause the updates, but that is not guaranteed. Okay. And you can finish the perceptron algorithm, find a classifier without finding these support points. So it's slightly different in this linear perceptron case. Sure. So, okay, great. So this is the margin, and this will be helpful, important for understanding why the perceptron algorithm works. In particular, we're going to be looking at the max margin, and we're going to be using this as a parameter in analyzing the perceptron algorithm. Okay, there isn't a, if there's not linearly separable, there is not a max margin because you can't, because the value here would actually be like negative, because there wouldn't actually be a classifier here. Okay, but for separable points, we're going to use this max margin. The bigger the margin, the easier it will be to solve the perceptron algorithm. It will run in fewer steps if the margin is large. Okay, and that's the margin after you've assumed all the data points are going to be inside a unit ball. The norm is going to be 1. Otherwise, I can multiply all the points by 2, and the margin goes up, but so does kind of the largest norm of any data points. Okay. All right, so let's talk just a little bit about why the yeah, great. So let's talk a little bit about why the perceptron algorithm works. Yeah, let's start again with an example of what's going on here. Let's see here. Okay, so try and, okay, so the perceptron will give a classifier which has to go through the origin. Let's kind of run through an example here, and let's say I'm going to try and make this a little bit challenging here. So these are going to be all of the negative points, and let's say the positive points are here. Okay, and you kind of see there is a linear classifier that is going to separate these points through the origin, but I've made it so it's going to be kind of a tight squeeze. Okay, so we'll start with this point. Let's say, let's start with, say, this point over here. So this will initially be, so W, and we can see it's not this is not giving us a perfect classifier, right? It's actually, the separator is orthogonal to this W, right? So this is not a great start. So I can now identify another point which is misclassified. So let's say this point is misclassified. Okay, so what I should do is I'm going to subtract this vector from W. Okay, so W is a vector here, and the new W is subtracting this vector. So now this is W after one step. This is now the normal direction after one step. Okay, it's slightly improved now, actually. I think was, oh wait, no. I did that wrong. That point was classified correctly, right? So that would not have been a good choice, because if I looked at this point would have been classified correctly before, so that would not have been a good choice to add. Instead, okay, so let's pick this point over here. This point is incorrectly classified, and there's a vector pointing to this point. I'm going to subtract that vector from W, right? And that's going to give me a new vector here. right? So this is my new W after one step. So after the second step, this is my new W. Okay, and let's see how this one is doing. Now, or my, okay, so now my classifier is here, and it's pretty good, but it's missed. Now there are 2 points which are misclassified. This point is misclassified, this positive point upper left side, and the negative point bottom right. Okay, so let's pick one of these points. This point here is now misclassified, so I'm going to take this vector and I'm going to add it to my choice of W. Right? So this is now, I'm going to update. This is my W after 3 steps. Okay? Well, how did we do? It looks like all the blue points are correctly classified, but one of my red points, actually the initial one I picked, is now misclassified again. This can happen. A point was misclassified. So I'm going to have to pick this point again. And this first W1 vector, I'm going to add this back here again. And this is going to give me maybe another vector right here. W4. Now, let's say it did. Okay, it's almost done. I have maybe another misclassified point here. Now, this point is misclassified. So I want to subtract this vector. I made the margin small, so that's why this is taking a lot of steps here. And now this is W. This is still some misclassified points. Let's take this one, this vector, and I add this back over here. And now maybe I perfectly split this. Okay, if you keep running it, it's going to kind of zigzag. It might zigzag a bit, but eventually it will get far enough out, and the changes will be smaller, and it will eventually kind of split through this margin and get a perfect classifier. But intuitively, this is how it's working. The W vector is kind of starting moving in the right direction, and it's getting further and further from the origin, and so that's forcing the step sizes to be smaller because all the points have a bounded norm. And eventually it's kind of, it's going to find a perfectly, a perfect separator. Okay, so that's, okay, hopefully that, again, there's, hopefully gave a little bit of concreteness to how the algorithm would run in practice here. There's a slightly more refined example in the book that I didn't exactly copy, but that one took 3 steps and it ran. Okay, so let's. Okay, so I'm going to claim that the perceptron finds a perfect classifier in. It's going to be 1 over gamma star squared, so updates, okay? 1 over gamma star squared updates. So that means if the margin, like the margin, remember all the points are shrunk within a unit ball, so the margin is less than 1, okay? And if the margin is large, let's say 0.3, then I'm 1 over 0.3, which is about roughly 3, and 3 squared, so 9 steps. If the margin is 0.1, then it's 1 over 0.1, that's 10 steps squared. So it's after 100 steps, it has to find the classifier. If it's the margin is 0.01, then it's 10,000 steps, right? So if the margin's really small, it might take a long time. And the example I had here, you know, if these are all in one, the margin is probably less. It's probably in the order of 0.1, 0.05. So that's why it didn't exactly terminate after 5 steps. It might have taken 100 steps to guarantee it was completed. Okay, but it will complete in number of steps that only depends on the margin. It does not depend on the dimensionality of the data, does not depend on how many data points you have. It only depends on the margin, how many updates you have to do. Okay, so this is kind of a pretty cool claim. And let's we have 15 minutes, you know, probably in 10 minutes we can prove this claim. Just a couple of steps of algebra. Okay, and I'm going to look at 2 quantities. So there are going to be two quantities we're going to look at. One is going to be W, which we find, compared to W star. Okay, and I'm going to show that that this quantity is going to be greater or equal to T. That's the number of steps times gamma star. Okay, we're going to show that this is greater or equal after T steps, right? So for T steps, okay, that the dot product between W and W star, that's always going to be growing, and it's always going to be growing as a function of the margin, T times the margin. It's going to be at least as big as that, right? Remember, W star is going to be normalized. W star is going to have a norm of 1, but W is going to be growing. I don't normalize that until the end. Okay, the other quantity that I'm going to look at is going to be just W, the norm squared of W. These are kind of comparable to each other. One is, that's the inner product of W with itself, right? W dot W. And this quantity, I'm going to argue, is going to be less than T. Okay, so this is going to be less than the number of steps. Okay. All right. Once I have these 2 properties, so once I have these 2 steps, these 2 things, I can say that T gamma star is going to be less than or equal to the inner product between W and W star, which is less than or equal to W times W after it's been normalized. Okay, so this step, I know I maximize the dot product with, if I can maximize the dot product of W with any some sort of unit vector, it's maximized with the unit vector in the same direction. The dot product is maximized if it's W times the dotted with the unit vector, maximized when it's in the same direction, because it's the length of the projection. Okay, so it's always greater to maximize by itself. And I know that this quantity is equal to the norm of W, right? Because if I do W dot W, that's the norm of W squared, but I've divided by the norm of W. So so I get this, and I have a bound here that this is less than square root of T, right? That's from this property, which I haven't proven yet, okay? Okay, so if I have both of these properties, then I can solve for t has to be less than or equal to 1 over gamma star squared, right? So I divide through by gamma star and by square root of t, and then I square both sides, right? And I can get this quantity. Okay, so if I've taken t, if I've done t updates, then right, so and these two properties hold, then I say that t must be less than 1 over gamma star squared. Okay, so so if I have these two properties have to hold after t updates, I must have t less than this number of steps. The number of steps must be 1 over gamma star squared. Otherwise, then if this is not true, then something is broken. Okay, so if both of these properties hold, then t must be less than 1 over gamma star squared. Okay, so and so if I can't do any more steps, right, then right, so so this would be saying if I did more than this many steps, I would have broken something. So I'm going to prove that those two quantities must hold, and if that is true, then this gives me a bound on the number of steps. Okay. Okay. Let's talk about these two properties. They're both fairly straightforward to show. Okay. So let's just look at one update. Let's look at W plus yi xi dot W plus yi xi, right? So this is an update with a misclassified point. Misclass xi and yi, right? So if I updated W with the misclassified point, I'm just adding that point to it, okay? And so I can expand this by the linearity of the inner product into yi is going to be a scalar. I can plus 2 yi w times xi, right? So if I just expand this out, right, the yi xi dot yi xi, I can factor out the scalar, which is always going to be 1, right? And so this is going to be less than or equal to w. This is the old quantity, okay? Plus the second term is less than 1 because yi is always 1 or minus 1, so that term is always 1. And xi dot xi, well, that's the norm of xi squared, but I know the norm is less than 1, so the squared norm is also less than 1, plus 0. This last term is always negative, so it's always at most 0 because it was a misclassified point. I only updated with misclassified points. Okay? So after one step, the inner product increased by at most 1 of W dot, so W, and so then by induction, because the first step was choosing one of the points which had a norm at most 1, after t steps, I am inductively increasing by 1. So so by induction, after t steps, I have W dot W is going to be less than or equal to t, right? So which is this property. Okay. All right. Let's do the other one. the other thing is now I'm doing W plus yi xi dot W star. Okay, and now I'm going to give a lower bound on this. This is, if I expand this out, it's W star plus yi times dot xi W star. Okay. Okay, so I've just expanded out this quantity. And what do I know about that? The second term there? Well, I'm comparing now a data point with the max margin, and I know that this term has to be greater or equal than W star plus gamma star, right, which is the max margin. That point was at least as far away as the margin. So that means that W star has to be growing sufficiently fast. Okay, so then after T steps, I have that, this one is going to be greater or equal to T times gamma star after T steps, because each step increases by at least gamma star. Okay, so I'm getting closer and closer after I've kind of normalized. When I do the normalization, so I'm kind of comparing it to the length of the vector W itself, that it's getting closer and closer to the max margin, the direction of the max margin. And how close is it getting? Well, that ratio, once I've normalized by doing this blue algebra, the ratio ends up being related to 1 over gamma star. And if I can't do, and all the updates were on misclassified points, so if I can't do an update, I must not have misclassified points. But if I do updates, then I can only do this many, otherwise I break something in the algebra. Okay, great. So let's, so kind of, not maybe you'll stare over the algebra. Sometimes it takes a little bit to kind of sink in. There's a couple of algebraic kind of manipulations going on. But the main point is that, let's go back and look. The Perceptron algorithm, it's going to assume that it goes through the origin. We can do this by adding one coordinate. It assumes all the points are less than 1. This allows us to define a scaleless parameter for the max margin. All right, that's all this second thing does. And it needs to be separable, because if it's not separable, it might go into an infinite loop. Okay, and we'll kind of solve this in the next lecture. Okay, then the algorithm itself, the Perceptron, is very simple. It takes a data point and it finds a misclassified point, and it adds the kind of yi plus the data point, right? So it goes towards a positive misclassified point or away from a negative misclassified point. You want it to point towards the positive points and away from the negative points, that normal direction, right? And because we've removed the offset, we have this nice duality between the data points and the normal direction of the classifier. We can really think of them in a similar way here. Okay. And then once we have this margin, we can define the margin, the minimum distance between any point and the decision boundary. We can consider the maximum possible margin. And the Perceptron runs in the number of updates that depends only on 1 over the max margin squared. Okay, so independent of the number of data points, independent of the dimensionality, only depends on the margin. So this is kind of a really cool property. The max margin classifier should be more robust to noise in the data and should generalize better to new data. And there's other analysis beyond what we'll cover in this class that has kind of quantified why this is the case. All right, great. So we'll stop here. Again, the quiz on these 2 lectures of classification and clustering is going to be on Thursday. But we'll also talk about nonlinear classifiers, SVMs, generalizing kind of these ideas on then as well. All right, so see you all on Thursday.